This is the ninth installment of Advanced J1939. In this installment, we'll continue looking at data. In particular, we're going to look at something called number bases and how we're able to take this information that we see from that we actually read from the oscilloscope, or we read from some sort of a CAN logging tool, take that and determine what actual data is. By data, I mean things such as engine speed, rail pressure, transmission, desired and attained range, etc. All the information, the things that you would see in a service tool or you would see on a display that was plugged in to the J1939. So looking at this real signal, we can see that we have the start of frame bit, which is a dominant bit. This is a logic 0. This is not counted as a 0. This is just telling everyone on the bus for, in this case, a 500K CAN bus, 2 microseconds that I want to use the bus. And we have the first bit then of what we would call the priority. And the priority, as we talked about, determines who wins an arbitration, supposing that two or more controllers started communicating at exactly the same time. So once one controller has put this start of frame bit out on the CAN bus and issued this dominant bit, nobody else can communicate. Nobody else can start communicating. So the first thing, as I indicated, we have the priority. This is part of the identification fields of the message. We'll go into some more detail of that, but in this we can see that we have the first bit is a logic 0. So this is, and Pico has picked this up. The Picoscope has determined that this is a logic 0, and it is the first bit of what we would call the priority. So this first bit of the priority, because this is a 0, indicates it's a higher priority message than some of the other messages. So this could be something like engine speed, or something dealing with torque speed control, or something like that. So in this message, we see that we have the first bit as a 0, then we have a 1, then we have a 1. This whole field makes up what we call the priority field. And so the first 3 bits of this J1939 message are to determine who's going to win arbitration, who's got a more important message. Granted, you could have 2 controllers start at the same exact instant with the exact same priority of a message, or 2 or multiple controllers. The next bits, or the fields of the message, would then determine who's going to win or lose arbitration. Once again, it starts another session of this where we have this other part of the identification, something we won't go into a great detail of, but at this part of the identification, it tells how important the actual message itself is. So this is the priority of the message. This is, if we take all the messages and line them up, it's like this message starts with this, therefore it has a higher priority. So that's all determined as part of the SAE J1939 specification. This is what the manufacturers agree on, and this is why you can kind of plug and play with CAN, and it should work. You can plug a controller in as long as it's supposed to be there. One that it's so looking back at the message here, the priority. So we see this is 011. Well, for electronic controllers, for devices which are digital, for microcontrollers, this is the language that they speak. They speak this 0 or 1s. It's 1 or 2 states. And as we said, it's either the data link has a difference of about 2 volts or a difference of about 0 volts. And those correspond to the 0 and 1, respectively, the dominant bit and the recessive bit. We talked about quite a bit. So looking at this as a human and not as a microprocessor, I need to know what 011 is it is 011 in binary. I want to know what that is in a number system that I'm used to. So the number system that we're all used to is something called decimal. So if I were to go down here to binary, I'll put this Windows calculator in binary. You can see when I do, there's only 2 values that it allows me to enter in, a 1 and a 0. That's all you can have for it. So let's see what a 011 is. Well, in decimal, this number system that is base 10, you start counting at 0 and you go up to 9, and then you add a 1 in front of it and it becomes what we call 10, right? And then you do that again, 11, 12, 13, and so forth. This is the thing that we humans can look at and we can understand. So if you were to tell me that the priority of this message is 3, and I look at another one and the priority is 6, I'm going to know that the message that has a priority of 3 decimal has a higher priority, is more important than one that has a priority of 6. So kind of let that sink in. It's like golf scores. The lower the number, the more the better that it is, the more important it is, we'll say. So why do we use this binary? Well, the reason we use binary is because that's what the data link has on it. It has that information, and it's either a 1 or a 0. Us humans, we need to transfer that into something we can read. We put it into something called decimal. The other, as we see, as I set the calculator to decimal, now I have all of these digits that are enabled. Another base is something called hexadecimal, and the word hex means 6, and the word decimal means 10, so it's 6 plus 10 or 16. So this is a base 16 system. You might ask, why would we look at it in that form? I'll show you here. Let's take a look at this data. I'm going to take the data, and we're going to take it and we're going to convert it. Pico has a way here that's pretty cool to display. Let's change everything in the graph format to decimal. And I'm going to go ahead and put the stuff down on the table in decimal, and let's take a look at finish. And there we go. Lo and behold, I can see now that the ID has a priority of 3. And they've converted, just like that Windows calculator, they've taken the 0 and 1, they've converted it to 3. However, if I look over here, I can see that I've got something here, this ID, this is something called the PGN, the parameter group number, and it has a decimal value of 61443. That's really hard for somebody who works with CAN logs and works with CAN to look at it and to say, oh, this is the PGN. I know that PGN, 61443. I have no idea what 61443 is. However, what I do know, and this is a lot of the specifications are written such that they're in a format called hexadecimal that we talked about. So I'm going to change both of these to hexadecimal. And when we do, amazingly, I can see that the ID still has a value of 3. However, the PGN is a value of F003. And I recognize this as being, I know this particular message. Anybody who looks at CAN a lot knows this message. For sure, they know this one. This is one F004. This is one that has engine speed on it. So if I were to look at this message, we'll pull it up, and I were to look into it, this is engine speed is contained within this, as well as a lot of other information. So this is the format that if you get a CAN log or you look at a CAN log, you're going to see all these Fs, and you're going to see things such as this. What I'd probably tell you to do if you want to learn hexadecimal, one of the easiest ways is get this Windows calculator, and you can take it over here to this form. So let's set it in this form, which is in binary. I'm down here in binary, and I can shift bits around. So I'm gonna look at this, and you'll see why we use hexadecimal. Hopefully this will make sense. So if I set each of these bits, so this has a value of 1111 in binary. I know that is decimal that has a value of 15. Anybody who works with computers, has worked in anything with electronics, anything digital, knows that 1111 has a value of 15. So this is, we can look at this. This is half of a byte, right? It's 4. I think it's called a nibble. But let's take a look. Let's go ahead and fill out the rest of this where we have 8 bits. And the reason we use hexadecimal is this works very nicely because it's base 16. When I have something that is 8 bits in length, and here's a value which is 8 bits in length, that gives me a hexadecimal value of FF. In decimal, it's actually 255. The reason Windows calculator does this, it treats it as though this first bit is a sign bit, and it then says that means it's a negative number. I don't know a way to change the Windows calculator. I don't need it to show that way. To be honest, this is a reason a lot of people get confused working with binary, working with hexadecimal, and things like that. I don't know if this is a sign bit or not a sign bit. That this kind of thing gets very, very confusing. There's no reason to even do that. So we're not going to talk about that no further than that. The reason we use hexadecimal, though, I want to show this, is that it allows us to see something that is a byte. So 8 bits can be represented. I can represent 11111111. I think I got all 8 as FF. It's a lot easier to write. It's a lot easier to read. I can look down here at the data, and it's like, yes, I know what this data is. And this is what you'll see on some CAN streaming tools or something that's a CAN log. For the most part, anything you're going to see is going to be in hexadecimal. There's a lot more reasons that we use hexadecimal, and the more you use this, the more it'll make sense. But if I take this and I put this, I'll go ahead and put this in binary. We'll put the data down below in binary, and we'll put the information that came off of using hexadecimal, or came off of this message in hexadecimal. So looking at this same message, we can see the priority is 3. The PGM, this parameter group number, what group of parameters are in this? Parameters are things like engine speed, coolant temperature, battery voltage, things like that. They're in a group. So each message typically has several related parameters contained in it. That's something we'll talk about more as we go on. But if you look at this for anybody that looks at CAN data, this is easy to read. This is pretty much impossible. I would really struggle with reading this and knowing what this is other than the priority. I mean, I could see that that's a 3. I know that's a 3. I look at the rest of this and I cannot do this in my head. Definitely not with the data. There is a lot of 1s and 0s there. Granted, that's exactly what's transmitted on the CAN bus. But what we do is we take those, and each of those is 8 bytes of data, and you can see that we represent that by each byte of data by 8 of these bits, and it's much easier to look at this and see in this format and see that this group of 8 bits has a value of F0 in hexadecimal. Whereas down below, if I were to look at that same group, it's like, man, that is really hard to pick out of this. I think it's this one. It's like, I don't know that that's. I guess I do. That's an F and that's a 0. So in that one, yes, I do. But it gets difficult to read, and that's the reason that we use this number base called hexadecimal. There are plenty of really good information tutors out on YouTube and other places where they talk about number bases. I'm not going to go into that because it is a lot of math. It's not something that I really want to cover. I'm definitely not great at teaching that stuff. My wife is a high school math teacher. She would criticize me based on my performance with that. So that is something she definitely knows. A lot of this other stuff she doesn't. So it's not something I want her to critique me on. So I'm not going to try to teach math. There's plenty of good sites out there that have it if you're more interested in this. So we'll talk more about the actual data. We'll talk more about how to take what you would see or what's seen on the CAN bus, take that and actually convert it into something which is meaningful data next time.